Okay, thanks again everyone to join a session on power system modeling with MATLAB. So basically, we will focus here more on power electronics. Okay, we'll start from the basics that how to design the rectifier. Then we'll go more deep and deep like this. So first of all, let's start from the application of power electronics, right? So electrical systems are used everywhere. If I'm talking about any industry, we can't imagine without, any plant or any industry without electrical system, right? So you see that here electrical systems are used in electric vehicles, if I am talking about, right? Yeah, or charging stations are there nowadays for electrical vehicles. Or if I am talking about rail, I cannot run without electricity, right? Renewable energy is there, lighting system is there. So more about we will talk about this lighting system. Just 1 minute. Okay, so lighting system is that headlights that sometimes you require to with a highlight, and with sometimes you have to low the light intensity, right? So these are some applications. Apart from that, there are vast applications if I am talking about power system in MATLAB. So, what is power electronics? Power electronics is the technology associated with the efficient conversion, control, and conditioning of electric power by static means from its available input form into the desired electrical output system. It means the power which we are getting from the source, the power is coming, the power which we are getting, we transform that power in a different form. In a different form means like we shape that, or maybe we use some kind of converter from high voltage to low or low to high. We shape that power. The power which we are getting, that is raw power actually. And every time if you see, there are some fluctuations in electricity. I mean, sometimes voltage is low, sometimes voltage is high. Direct, if you are going to use that power in any electronics devices or any kind of like AC if I am talking, or if you have a refrigerator if I am talking about that, direct if I use that power, there's some kind of noise will be generated, like common mode or differential mode kind of noise. And once a noise is generated, your system will be shut down, it can be breakdown. So that is very important to design a converter to get the constant voltage at every time. Okay, so and why power electronics? At the worldwide average rate of 12 billion kilowatts every hour of every day of every year it is generated, and more than 80% of the power generated is being reprocessed or recycled through some form of power electronic systems. 80% we reprocess the electricity which we are getting from there. It is estimated that the power wasted in desktop PCs sold in 1 year is equivalent to 17,500 megawatt power plants. So we require to design a such kind of power electronics, so it will be a energy efficient, and the losses which is going, and we have to reduce that losses. So it is estimated that with the widespread use of efficient and cost effective power electronics technology, the world could see a 35% reduction in energy consumption. That is very important to save the energy in the current scenario, right? So you have to be a we require a good engineer, so who can design a perfect and power efficiency power electronic systems, right? Why Simulink for power electronics? We in MATLAB in Simulink we have extensive libraries of sources and loads like PV arrays, batteries, motors. Broad range of power electronics models are available, like average value, fast ideal switching, physical based, or if I am talking about converters, motors, machines. Already libraries are available there. Advanced control design capabilities. Controlling power is very important if you are designing the converter, that how you are going to control the output from the electrical system, the power system, right? So we have modules available like auto tuning in time and frequency domain for single and multiple loops, generation of readable, compact and fast code from models. So not only designing the system is important, testing the system is also very important. So once you test the system and you are getting the desired output which you want, and further you can deploy in a hardware. So in MATLAB, it provide a complete solution from model in the loop to the hardware in the loop. Model in the loop means the model which you are designing in Simulink and testing that. Further, you are generating a embedded code or FPGA code, STL codes, and you are testing that codes. Then processor in the loop means you are deploying your controller in the processor or in the controller hardware, and you are testing the controller. And further, hardware in the loop means you are testing with a real plant. Once your testing is fine, various testings are there. Once your testing is fine, then you can launch your controller or system in a real time, in a real world. You know that right now COVID vaccines so many labs are making, but still it takes time. So because testing is very important, you require a accurate model. If I am talking about a power system, right? So these are some libraries which you see in MATLAB, like control libraries are there, electromechanical libraries are available, specialized power systems libraries are available there. If someone is working on renewable energy, we have a PV array, we have a wind turbine, double fed, different kind of wind turbine which exist right now. We have libraries available for that in Simulink. Apart from that, we have RLC circuits available, RLC loads are available. So it depends on you. We have machines, synchronous or asynchronous machines available there. Induction machines are there, induction motors are available there. Depends on you that what kind of applications you have. You can use these blocks to design your model. Even maybe you require some blocks which doesn't exist. So in that case, you can design your blocks also. Okay, let's start from a simple model, from a half wave rectifier. From rectifier we are going to start. This is a rectifier electrical circuit which you see here, right? For rectifier we require voltage, we require ground reference, we require diode and the load, right? So we will start from the half wave rectifier, right? So let's start from the basics, and first I will show you libraries also, what kind of libraries are available here. Here you see, already we discussed yesterday that these are the part of the Simulink. So you know that two ways you can design any kind of physical system. You can use these libraries of the Simulink which I am talking about, or you can use Simskip, that is this library. So this is a part of a physical modeling, and this is a part of a Simulink modeling. So what is difference between Simulink and physical modeling? In Simulink, your signals will be one directional only, and if I am talking about physical modeling, that is a energy signal modeling. In that case, your signal will be bidirectional. For example, in electrical system, current is bidirectional, right? So depends on you. If you have a mathematical equation, or if you have a transfer function of your system, then you can go for the Simulink modeling. Okay, so two ways we can model. Another is that I don't have a mathematical equation, but I have a proper insight of a physical system. I know the insights that resistance, capacitance, if I am using op-amp, or if I am using machine, then what parameters value will be. Then you can go for electrical system, this physical modeling. So here also you see that if I am talking about Simscape, so we have libraries available, drive line, electrical libraries. Somebody is working on mechatronics, so you can integrate multi-body with electrical, Let's say what in multi-body libraries do we have here. So you see that this is a 3D modeling. If somebody is working on robotics or mechatronics, you can use this uh, libraries for that. And you know that these libraries which you see here right now, these are the gaseous libraries. Someone is working on gases plant, hydraulic, isothermic liquid, magnetic, mechanical, right? These libraries are available for different systems. So the good thing is that you can interface one domain with other domain. Okay, someone is, as I told that if you want to use some mechanical components, and if you want to use with electrical components, like to design a DC motor, very simple example, so you can use these libraries with that. Okay, the mechanical libraries which you see, it will be shown as a green. Okay, electrical libraries will be shown as a blue, so always remember. So here you see that blue and green both are there. The blue means electrical part and green is the mechanical part here. So this is the DC motor, you may say. Okay, some advanced libraries if I am talking, then let's move here. This here we have a advanced electrical libraries available here. So let me explore that. These are the connectors and references basics. These are some control libraries available here, like BLDC control, converter control, general motors are available here, right? So these are advanced libraries. If I go in electromechanical, so in this case, see, we have asynchronous motors machines available, right? Induction machines are available here, and these are brush motors. So all components which you require to design a electrical system, we have libraries available here. Someone is working with integrated circuit, so we have blocks available for the like CMOS and or not. And here you see push pull output, comparator is available there, right? Multiplier is available there. Semiconductor and converters, if I click here, you see that IGBT, MOSFET, and channel IGBT. So switches are also available here, and rectifier is also available, right? And if I explore this more, and you see that for if you are working on power electronics, already inbuilt converters libraries are available there. Here boost converter, buck boost converter, right? Different converters are there here. Sensors and transducers are available here, blocks. Okay, apart from that, if somebody is working on special power system technology, that is second generation of electrical system. So here you see that facts are available there, transformers are there, right? And fundamental library, if I go, these are the sources which you see, right? These are the elements here which you see right now. These are the elements, like someone is working on series RLC circuit, or someone is working on transmission line, so pi section line is available there, right? So different libraries, a decoupling line is available there. Apart from that, if somebody is working on renewable energy, we have arrays available, PV array. Somebody is working on wind generation, we have. So we'll see these examples also, that how to design this kind of things. So first of all, the important thing is that what basic things you require to design a physical system, right? So we will start from a simple model that is called rectifier. Okay, so what I am going to do, first of all, you have to open the Simulink by giving this command as a Simulink, or here is the option to open a Simulink. So both way you can open the Simulink. A window will be open like this. So this is the model which we are going to design. This is a part of a Simscape. So we will scroll here, and simple Simscape. There, see, there is a generic Simscape, electrical, three-phase, gaseous. So we are going to use generic Simscape in this case. So once I click on this, whatever basic libraries we require, it will be here already. Fine. The basic library which we require. So we have to design a half-wave rectifier right now. So we require a diode, resistance, power, right? So I am going in library browser, and I will go here in electrical components. So from here I have a diode available here. I will right click and I will add it. We require resistance also, right? So we will add this resistor here, this one, and we require a reference. We are going to add this. Okay, we have all these libraries. Now let's now we require a source. I am going to use control voltage source. Perfect. So here we have all libraries. So let me increase the size of all components which I have right now, so it will be visible for you. Okay, this is the ground. Okay, so I have this also, and this is the power which I am going to use, that is a voltage control source. It will be this is a voltage control source, so it will be controlled by the different signal. Okay, we will provide that signal, and resistance we have to add it. Let me rotate it and add it here. So we have this resistance, and here this is the connector. So like this you can connect, and from here I have to provide the external signal, so voltage will be controlled. So right now what I am going to do here, I will go in library again, and from here sources I am going to take a sine wave to control that. I added here, this is the sine wave. So you know that this sine wave is from the Simulink. It will be not connected directly here. You see, this is the problem, it will be not connected. So in this case we can use this converter, this converter which you see here, this one. This is a Simulink to physical signal converter. So what we will do, the arrow which you see, this tail will be added here, and this will be added here. Okay, now it is connected. So this color shows that this black color shows that this is the part of a Simulink. The signal will be Simulink, and further it is converted as a electrical signal, that is a physical signal, and we require one ground here. Okay, now we require a sensor to measure a data, I mean voltage at the output on this resistor. Apart from that, if I click on this diode, depends on you, do you want ideal diode or forward voltage? What will be a forward voltage for that? If some resistance and conductance also you can provide for this diode. So here you can change the parameters if you want. If I click in variable, initial current is what in that diode, and initial voltage is what there. Also you can provide it. Apart from that, let's say that this diode you want to modify. Let's say I want to modify this diode. So what I can do, I can just go in the source code, and from here you see that this is the source code for that block. So here if I want, I can modify as well this code. Once I modify it, then that block will be modified, right? So you have to save with a different file name, because the inbuilt libraries which are available in MATLAB you can't modify. Save with a different name and you can modify. And here you see that what unit are you going to provide. So that's options are also available as a ohm or kilo ohm. So depends on you. So same for the resistance also. Here you can provide what is the resistance. Let's say it is 100 ohm. Okay, now about electricity. Let's click this sine wave. I want amplitude will be 250 or 100. Let's say this is a max voltage, right? Amplitude will be a max voltage, and frequency I want 50 Hertz. This is the frequency. Okay, now to measure output. So if you have to measure the voltage, then you will measure the across of this load. If you have to measure the current serially, you will connect somewhere else. So before this, let me show you an analogy of this, right? So that if you are working on mechanical system, what will be in serial and parallel and what will be as a across, right? That is very important. So see here, this help is already given in the this system, I mean sorry, in this documentation. So for at the electrical, voltage we measure across, current we measure through variable, means serially we will add somewhere. Gas, in gas system, pressure will be across and mass flow rate will and energy flow rate will be parallelly or serially sorry, that will be through variable. Okay, so same way, if I am working on mechanical system, rotational, angular velocity will be across and torque will move like a current. So torque is an analogy of current. So torque will move. So torque, when you have to measure the torque, you will apply through variable. Okay, and if you have to measure the angular velocity, you will apply the across. This is the analogy of the voltage. So here all analogies are given in this documentation of MATLAB. So that is the offline documentation. Okay, I am switching here. We require sensor. So this is a part of again same escape. I will go in utilities. Let's say that if you don't know the block name, where it is, you don't know where it is blocked, so from here you can search it. There is an option to search. Okay, you can search it from there as well. Okay, we require a sensors, right? So we require a voltage sensor. I am going to add this. We have a both sensor. So if you want to calculate the power, you can use the current sensor also, and you can multiply that and you can calculate the power also, right? Okay, I have this. So first of all, I want to measure the voltage across this resistance. I am going to add it here. See the connection, in this case the connection is as a dot here, you see, and this connection is like point of pen, if you see like this. So from here we can visualize the output, and this is the across which we are going to connect. Now again one issue here, it will be not connected directly, so we are using this library that is called physical signal to Simulink converter. Okay, so now we connected this one. Perfect. Okay, let me remove this current sensor. I am going to run for 0.1 second, and let me run and check that what output is coming first of all. Okay, one thing more we forgot here to do, we have to add this solver configuration, because overall this circuit equation will be calculated as a mathematical equation. Okay, so we require to solve that mathematical equation. That will be an algebraic differential equation. So you can connect this solver configuration anywhere in this circuit. That's all, and our model is complete. Okay, one thing more here, I will go in the modeling. Let me explain. I am going in the modeling and I am going here in the setting. Fine. One thing more we have to do, if you remember about Runja-Kutta method to solve the ODE equations, as I told that a differential equation will be created. So for electrical system, we use this solver, ordinary differential equation with second and third order. And if you are working on special technology, second generation of electrical system, you are going to choose this one. And these other solvers which you see, that is a part of a Simulink. And right now we have a automatic solver selection. Based on your model, automatically solver will be selected. So I am going to choose ODE23T. And one thing more, what I want to do here, there is a two option, fixed step and variable step. So if I choose the variable step, automatically step size will be selected by the MATLAB compiler. And if I choose the fixed step, I can provide the what will be a step size. Means let's say that step size is 0.2. If I provide here a step size 0.2, what it means, first value I will get at 0, then at 0.2 time interval, then at 0.4, Whatever at point 4 we will get, it will be hold till point 6, then we will get points at point 8, right? So this way. So if you have a complex model, always use fixed step, otherwise variable step is fine. But what is the problem in fixed step? Let's say that step size is 0.2 and my first value will come at 0, and let's say between 0 to 0.2 there is any maxima and minima, that will be removed, because whatever value we will get at 0, t is equal to 0, at t is equal to 0.2, it till t is equal to 0.2 it will be holded, and between them if there is maxima and minima, that will be removed. So I am going to choose here variable step, and maximum step size I am going to give 0.01. My step size will be below this 0.01, so it will take a little time to execute because the step size is very small. So I am going to run this for 0.1 second. So you have an option to run from here, or you can run it from here scope also directly. So let's see that what output is coming here. So this is for the 0.1 second, the output which we are getting. So you see that this half wave rectifier which we here calculated, it looks discrete somehow because the step size is high. So what we can do more here, we can go again in this model setting, and from here maximum step size I will do 0.00. More I am decreasing, what will be a maximum step size, right? And let's check it again that it looks like smooth or not. Now you see it looks like it's smooth for 0.1. Okay, now what I am going to do here, in this time step I am going to run for 0.5 seconds, and we are going to check what will be a output. See the perfect half wave rectifier, we got it, right? Hope you don't have any question, don't have any doubt. This is the half wave rectifier. And what about full wave bridge rectifier if I am talking about? So I am switching here, full wave bridge rectifier. How to design this? So in this case, this is a circuit equation which you see, 4 diode we require. The red one which you see, it is active and it is passing the current, and blue from black one it is not passing, right? So this is the full wave rectifier. So for the time being I am not going to design it again, I have already designed. Also I want to use the transformer, I step down transformer here. So this kind of libraries are already available, and you know how to add that libraries, right? So I am going to close this, and I am switching here in MATLAB. Okay, and from here I am going to open a full wave rectifier. Okay, here we don't have, just 1 minute. See, very simple. This transformer is already available in this Simulink library. We have these transformers available here. We added this transformer. So you see that again we are using a controlled voltage source here. We are controlling from this sine wave. You see that total voltage is 250 in this case, right? I am using step down transformer here. So winding ratio is 1.5. Perfect. So and the voltage which we are using, that is 250. So 250 divided by 1.5, the voltage we will get at the output in, that will be around 166 volt. That is step down after providing the winding ratio. And this is the full wave rectifier here, which you see here. So for half this will be active, this diode will be active, and the current will flow through that. And for the next half this will be active and current will flow again here. From here this will be active and current will flow again here, right? So we will get the positive voltage all the time, right? So for 0.5 seconds I am going to run this again. So let's see that what output will come here. So perfect full wave rectifier we got. Now let's say that I want to convert this as a DC voltage, right? We want to convert as a DC voltage. Let's say that I want to convert in a DC voltage, right? So what we can do here, we can add one capacitor for charging and discharging here. So from here I will, if I go in this library, and we can choose one capacitor. So this is the capacitor which I am going to use. Perfect. And this is a sensor resistance here which we have. This is the resistance inside. Okay, this is the resistance we are using, 500 ohm. And capacitor is here. Let me rotate this. By Control R you can rotate this. When you press the Control R, and it will be rotated. Okay, so this is the capacitor. And here you can you can provide the capacitance value. What is the capacitance value? But exactly you have to know that what will be a capacitance value for that. Okay, let me increase this capacitance value here. Just wait a minute. So we have to know the proper capacitance value. If you know once that what will be a capacitance value, then we can convert it as a DC value as well. Let's say that it is a 10 farad or something like that, or 1 farad, it is something like that. Okay, and once we run this, we will get somehow, it's not a proper DC, but still somehow we got this, right? Okay, one thing more here. Let me remove this capacitance from here. Okay, one thing more I want to show you. As I told that the output voltage will be somewhere around 166. So you see that somewhere we are getting around 166, right? If I have to measure this, so if I click here, there is an option to cursor measurement, and we can measure the voltage as well, that the model which I designed, and at the output end I am getting that model or not. So you see here that if I move this somewhere here, here is the output, right? Not exact, it is at the peak one, but 1.5 we are getting. Or there is an option to find out the peak as well. Here, peak finder. So you see that it is almost 166. 1.65 into 10 to the power 2 means 165 volt at the output end. Okay, so this was about this. Let me close this one model. Okay, I'm going to close this, and I'm switching here. Fine, I am switching here in PPT. Next, power electronic system which we are going to do. So what is a power electronic system here? So let's understand first of all power electronic system here. We will have some input source as an AC or as a DC voltage, or unregulated input source also we can be. And here we will have a power electronics converters. So converters can be AC to DC, AC to EC, or DC to DC. So if I am getting input as a DC, then why I am converting again as a DC? I can use some voltage regulator to increase or decrease the voltage, but why we require a DC to DC converter? So I answered this in the previous slide, that whatever voltage source we are getting from wherever, doesn't matter, the voltage which we are getting from the source, there is always fluctuation, I mean high voltage and low voltage. So if there is a difference in the voltage when you give directly to your devices, so some kind of noise will be generated, and your system will start heating, and it will be shut down it will be breakdown. So converters are used in your mobile charger, converters are used in the fridge, converters are used everywhere where we require a constant voltage with respect to time. So here we require to design a converter, and this is the controller part. And here we are giving the some reference sources how we are controlling this load. I mean the voltage at the voltage or current at the load end. Okay, so there will be some sensors which will sense this output, right? There will be some sensors which will sense the output from here. So once the output is sensed, it will go to the controller, and there is a reference. It will be error will be generated. Error will be minimized by the controller, and that error controller signal will go to the system, power electronics converters, and it will try to control that. Okay. So challenges for power electronics engineer. If you are power electronics engineer, then what kind of challenges you can face, right? Understand the impact of the power source and load. So whenever we are providing the power and source, what will be an impact on the system? That is the big challenge. How you can visualize that, how you can understand that what kind of issues can come, right? Second challenges can be a testing for a complete range of operating and fault conditions. So let's say that I have a system which works between 15 volt to 200 volt, but I want to check with different variation of voltage that my power system is working or not. Because let's say that I have a PC, okay, desktop machine computer. So I have a PC, and let's say that and that PC require a 240 volt. Let's say that PC require a 240 volt, constant 240 volt, and the converter which I am using, it work between 100 to 250 volt. So let's say that if voltage is 100 as an input for the converter, and at the output end for the PC I am getting to 40 or not, at 100, at 120 or 200 or 240 volt, whatever voltage is changing from the source, but I require a constant 240 volt for my PC. This kind of testing is very important. Designing and implementing digital controls using only SPICE simulator tools, means integrated circuit simulation. We don't require mathematical equation like from physical system which we have to design. Catching errors during software hardware integration testing. Catch the errors during the simulation and during the integration with the hardware. Not only designing, testing part is also important, right? And the last, which is very important, that compliance to industry standards. So whatever, if I am talking about mobiles which we use, there is a FCC standards, that EMI, electromagnetic interference, which occurs with the mobile. So there is some standard that it has to be minimum. When you purchase a mobile, when you see there is a FCC standard will be written, and maximum EMI, how much your mobile is producing, and that EMI is very harmful for human. So there are some industry standards also, we have to compliance with that as well. Development time, of course, we require to design such model which will take less time, right? So this is the complete model which I am talking from developing to implementation, from design to implement this model. So here you see right now this is a Texas C2000 hardware, right? This is the hardware. This hardware can be installed in the headlight of this vehicle. So what we have to do, we have to design such kind of converter, controlled converter, from which we can reduce the light intensity, or sometimes whenever we want we can increase the light intensity, something like that. Maybe it is dark, I need less light. If it is day, somewhere evening, I want highlight, more elements, I mean that light, right? So in this case, this is a complete circuit equation. So what we are going to do, we are going to do analysis of this DC to DC SEPIC converter. So there are different kind of converters. Like if I am talking about buck converter, so what it does, high voltage to low voltage it gives constant. And there is a boost converter from low voltage to high voltage. Same way there is a buck boost converter. Sometimes I require a high voltage. I am giving 100 volt as an input, I want 200 volt. Or I am giving 100 volt as an input, then I want 50 volt only at the output. Constant. And that kind of things we can do using buck boost converter. This is the advanced SEPIC converter of buck boost. Okay. So you see in this we have two inductance. This is the gate from where we are switch, you may say, from where we are controlling this. Capacitor, here is one capacitor and one diode is there. So lots of people they do thesis on this also. They are doing PhD as well to improve this converter more and more to get the high efficiency. So workflow of power control converter design. First of all, first step is sizing the inductor. How we are going to size the inductor means what will be inductor value, what will be a capacitance value. So I will get the constant voltage at the source, at the load. Okay. Understanding the behavior of the continuous and discontinuous mode. So two modes we are going to see that sometimes let's say current is 0, still I am getting constant voltage or not. Or if I am getting the continuous voltage, continuous current, still I am getting that constant voltage as the output in or not. So two things are important. So if it is discontinuous, maybe for millisecond electricity is not there, or for a 1 second something happened and electricity it is fluctuated because of some reason. So in both mode we are going to check continuous and discontinuous mode. Okay, then design a control algorithm based on time frequency domain specification. So further, how to control that power electronics converter, we will see, we will design a controller as well. The complete system, I will show you how to design that things. Okay. And the last, implement power electronic controls on an embedded hardware. So we don't have a hardware right now. Even if I have I will be not able to show you from here. So workflow I will show you that how you can deploy in an embedded processor also this controller. Okay. So let's start from the sizing inductor capacitor and understand the behavior in the continuous and discontinuous mode. So these are the different kind of DC converter topology. So you see that I was talking about buck converters. It looks like this. This is a boost converter. This is a flyback. Cook converter. This is the SEPIC converter which we are going to do analysis on this SEPIC converter. There are some other different converters also. Flyback, two switch flyback, forward converter, two switch forward converter, active clamp converter. This is the topology of this all these converters. Okay. Some more full bridge, push pull, half bridge, phase shifted full bridge converters are available there. Okay, let's start to do analysis of open loop circuit SEPIC converter without controller. First of all, we will design a converter without controller and we'll size that capacitor. Okay, so this is the model which we are going to analyze. This is the system. This is the SEPIC converter. This is the circuit diagram of that. Some control, we are controlling this from this switches. So how to use these switches? First of all, we'll discuss how to do a rapid prototyping. Okay, to use these switches, how we are going to control any kind of system from these switches. Okay, so first of all, I am going to start the Simulink, and from the basic I will show you that how to use that switches, right? A very simple equation I am going to design here. Let me write that equation first of all. So if you have to write some text on Simulink, just click here and start writing. Simple equation I am going to write: y is equal to sine t plus 10. Okay, and apart from that I am going to add one signal also here, and let's say this is 10 sin t. Let me zoom it so it will be visible for you. This equation I am going to design. So this is some chirp signal which I am going to use. Let's say this is a chirp signal. we discuss first, right, what is the chirp signal. So this equation we are going to design. A very simple equation I have here. So for this we require a sine wave, we require one chirp signal, and one constant we are going to add it here. Okay, if you know the block name, just move your cursor and start directly searching from here. So once you search like this, we'll get that sine wave. So this is the sine wave which we require. Fine. Okay, we require one constant block. Just simply search here constant block and we'll get the constant block as well. And let's say that this is not added, this is subtracted from there. So we have this constant block also here, chirp signal. So plus a chirp signal is added from here also. So what will I do? If you don't know the block name, so you can get it from here. Sources. This is the chirp signal is sources somewhere. So let's see that we have chirp signal. So here we have a chirp signal, right? We are going to add this one also. Perfect. So we have this and we have this chirp signal as well. All things we have to add it, so we will get the y. So we require one sum block. So this sum block, if you know the block name, you can search it from here, or from library you can get it from math operation. So this is a part of a Simulink which we are going to design. So right here we have this sum block here. Perfect. Okay, we have this sum block, and three sub functions we have to add it here. So double click, two plus are there. I'm going to add one more plus. Apart from that, I want it as a rectangular. The representation of this as a rectangular I want. Okay, this is a rectangular, and now I am going to add this sine wave. I am going to add this one, and I am going to add this chirp signal. So in sine wave you see that amplitude is 10. Just double click on this, provide the amplitude from here as a 10, and you see that the 10 is subtracted from there, right? So instead of plus, 1 will be minus here, and just apply this and double click on this, and this will be 10. Sorry, 10 it will be. Perfect. We have this one, and we added everything here. Chirp signal, what is the frequency here? It is given. Target time seconds is this, frequency is 1 Hertz. No problem, it's okay. Okay, now to visualize this output, I will go in the library. We have a scope sub-level. Let me show you both way how you can visualize. So I'm going to use scope also from here. Okay, scope is added there. And another way to visualize this, just go in the dashboard and take this dashboard scope. Perfect. We have this dashboard as well, where we can visualize our output. This is the dashboard and this is the scope. So this is the output and this is the input port at the tail side. Okay, so we have this dashboard and we have all this system which we designed. I mean already we have done everything. We have designed this. I want to represent this system in an area. So here is the option for area. Just click on this. Just wait. Just put in a single area. So that is very good way to representation, that let's say that I have different subsystems, I can represent with area with a different color. So there is an option to format that area also. What background color do you want? You can change it also, right? Okay, this is the output where we can here we can visualize our output. So now it says that double click to connect. So when I double click on this, what output I want to visualize? I want to visualize the output from this line. So just I will select this line and you see that this is appeared here, right? Apply this and okay. Now I am going to run for 10 seconds. So you see that sine wave plus chirp signal plus 10, this is the output which we are getting right now. And same output we will get from here as well. Perfect. Okay, now about switch. I want to modify this constant with respect to time. I don't want to check with this 10 value also. I want to check my system output with different constant value as well. So I will go in library, and in this dashboard we have this rotary switch which we are going to use. Right click and add this here. So this is added here. It's saying that double click to connect. Okay, so I'm going to double click on this, and let's say if I'm choosing this, so it says that let's say I want to change the amplitude of sine wave. There is amplitude right now, it is 10. Okay, so when you select this, whatever parameters are there in this block, all will be appeared here. I want to change the amplitude, so I will just select the amplitude of that and apply. Okay, so it is right now, it is off. Then you can do like this. You can move like this one, high, medium, right? And apart from that, we have a different kind of switches also available. This knob, instead of using that, we can use the knob also, because here value we cannot see. It's showing only off, low, medium and high. So better, let me remove this and use the knob, right? Just wait a minute, it is still opening. So you can use the knob also if you have that kind of data. So you can use this also. Just double click again and select the parameter which you are going to change. I want to change the amplitude. Apply, and here you can provide the minimum value. Let's say provide the minimum value 1. Okay, done. When amplitude is 1, also I want to log this signal. From here I want to log it and I want to compare it later. Okay, so what will I do? I will select this and I will go here in the signal, log signals. So you see that something, we got a Wi-Fi notification here. So this output will be logged. Now I am going to run when this amplitude is 1, and I am going to run. So this is the output when amplitude is 1. Now I am going to check when amplitude is 28. So you see that now it is at 28 right now, and I am going to run it again. And I am logging that data as well. So where I can see this log data in data inspector. When I click on this, from here it is still opening. Okay, here you see that this is the first run. Sorry, this one. This is the first run, and my second run is already here. It is given. So this is the difference. So when amplitude was 1, this graph it was. When amplitude was 2, this is the graph, right? So like this you can design a complete model, and you don't have to manually change every time. You can log that data, and further you can compare it also. There is an option for compare, right, from first, third run and second run. So you can compare as well. Like I want to compare this. You see, this is a comparison. This is the first one, this is the second run, this is the last one run, and this is showing the difference. What is the difference between both runs? So like this is called the model in the loop. Like this we check our system. Now you see, I want to see this output with real time. I want to change this knob with real time, and I want to visualize the output that in real time. If I change, real time means in continuous running, not a real time, but it will run for continuous, and I will change this value and I will check the output. So for INF here I am giving, for the infinity loop I am going to run, and this is the model. So it will run for the infinity loop, you see, and from real time we can change, and I can see the what is going on, right? Let's say that right now I am going to use 91, and here you can see the changes, right? So this is a rapid prototyping kind of things also, that run your model for the infinity time and check that what output is coming from there. And once you are happy with that parameter, then that's all the parameter which you wanted for the output, right? So like this we use this switches and knobs. Now about this SAPIC converter which I was talking about here. No, not this one, just wait a minute. Okay, I was talking about this open loop SAPIC converter, right? This one, right? So let's do this things, how to control this. So I am going here and let me open that model first of all. So what we are doing that to check that for if my voltage is changing or then I am getting the constant output or not in that case. So here we are providing the 12 volt. Okay, so right now this is connected with this inductance. Okay, so right now the inductance value is 470 microhenry. Okay, and this is connected with this capacitor value. So what is the capacitor value? Somewhere 950 it is, right? Okay, so 947.39 something microfarad it is. Okay, so I have connected this SAPIC converter here. Let me run first time and check what output we are getting. And here you see that here we are using switch and pulse wave we are getting here, pulse with modulation. Okay, and the duty cycle we are providing from outside. 0.5 is the duty cycle in this case. This is the duty cycle. These blocks are already available in Simulink library. This is the asynchronous pulse wave modulation generator. This is the switch, how we are controlling this. Here we are measuring the current, serially we added here, and across we are measuring the voltage. So right now you see that we are getting voltage somehow here, right? And let's see that it is continuous or discontinuous. So from current we can check. So let me zoom this. So from here you can zoom here, just click on this and zoom this. So that is continuous, right? We are getting the continuous volt here. This is the continuous mode. Now discontinuous mode. Let's move this. Let's change the inductance at 10. Okay, somewhere here around 10. Okay, now I am going to run this again. And so you see that we are getting here constant voltage. There is no change in this voltage, right? Somewhere around 25 we are getting here. So this is boosting right now because of this controller. It is boosting because 12 volt we are giving, and we are getting around 20 to 25 volt, right? Okay, so it is still running. And let's check the current right now, and let's check that it is continuous or discontinuous. So I'm going to zoom it again. Let me zoom this. You see it is discontinuous mode. Why it is discontinuous? It is going to zero as well. So whenever we have a sometimes current zero, still we are getting the constant voltage at the output end. Perfect. So this is a sizing of capacitor and inductance, that how we can do a different sizing and how we can check. So this is a discontinuous in this case, and still we are getting the proper voltage at the output end. Perfect. Okay, so I'm going to close this, and you see that here also we are logging this data. So when I go in the data inspector and just 1 minute, this run. Okay, third one. I have to untake this one, so that's what I am checking that in which run it was. Okay, second run. Here it is. Okay, so you see this is the output which we get. Okay, it is not disconnected right now. Okay, this is the output. Here you can log this data, and this is the first run, right? Last one run, and the second last when inductor was somewhere 270. So this is the value in that case. This is the first one. This is the second run. This is the last run which we see. So this is the difference which is showing you, right? You can compare it also again, like we did before. This is the sixth run. This is the fifth run, and you can click the compare, and you can compare it as well from here. Fine. Now you got that running the model and change how we can size the capacitor or inductance if you want, and we can do analysis on different capacitance inductance values, how we can check the output here at this end. Fine. So now we are going more advanced for closed loop. So I'm switching here in PPT. Here is that. Let me minimize this. Okay, we saw this, and next recap. Let's what we have done till now. Use simulation to design DC to DC converters. Optimize component sizing using simulation drive analysis. So optimize, we size the capacitor, I mean for the required output which we wanted, but we can use the closed loop system also. We can design the controller also to control it, this pulse width which we are getting here. So this is the complete model which you see with the closed loop. So why it is closed loop? You see that from here we are getting the output. This is the voltage sensor, and it is measuring the voltage, and this is the microcontroller. Okay, it is going as an input here, and this is my reference which I want, desired output. This is the desired output which I want here, and simulated output. It will be subtracted from there. Error will go to the controller, and controller will try to control it, and this is the switch again here. Okay, so let me move here. Before that, let me close everything which I have opened here, and I am going in Simulink here, this model which we have right now. Okay, this is a model which we have right now. Fine. Let me run this model and check that what voltage we are getting, and you see that the reference which we are getting, that is 0.4 volt. Fine. And if I go in the microcontroller, if I go here in this one, and this is a PID controller which we are going to use. In PID we are using the PI controller. So here you can choose that what kind of controller do you want. So in the case of PI controller, this is the KP value, that is 1, integral KI value, that is also 1 in this case. Okay. Now I am going to run this model, and I want to check what output I am getting here. So this is a complex model, so it will take a little time to execute. See, it is dropping to 0. You see here, this is this red color, this color which you see, that is the desired output which we wanted. And this is the simulated output. It is coming near around somewhere 0. Means the output which we want, we are not getting in this case. Even it is not going up either, right? So there is a issue, right? So we can tune that controller to get the desired output. You see here, output is connected, simulated output, and the desired output is connected, which we want here, right? So what we can do, we can go here, we can go in this controller, and from here there is an option to tune it. Let's click on the tune. This is the auto tuning kind of things. So it is still opening. What it will do, it will try to linearize, because you can't represent a non-linear system as a transfer function. So it linearize, then it will be open. If it is not able to linearize that system, then I will show you how you can tune that plant even if it is non-linear system. Okay. So this is a auto tuning app here. So from the controller we opened this auto tuning app for the PI controller. So it is still opening. Now you see that here what is written, plant cannot be linearized, the issue we got. So what we can do, we can identify the system, that what kind of system that is. So for to do that, we will go here in plant, identify the new plant. Means we are converting as a transfer function. We are going to measure the input and output of this system. Means the system which we have, you know what is the transfer function of any system? Just simply output by input. The same thing we are going to measure and we are going to tune it then later. So here is the option, get input output data. So simulated data from the Simulink itself, I am going to take that data. Okay. So here we can see, here it is saying specify U is the input for the plant and E is the error, right here. So perfect. Okay, run this simulation. When I run this simulation, automatically it will calculate the input from that electrical system and the output also from that electrical power system. So it is simulating. It will take a little time and it will give me a input and output of that. Okay, one thing more we forgot to modify here. We had to provide the step time. What is the step time here? Okay, here we have an option that this is the step response we are choosing. Input as a reference we are giving as a step response. Here we have to modify that what will be amplitude of that step. We forgot to provide that, right? So no problem. So meanwhile, if you have any question, you can write in a chat box. If you have any question, just you can write in a chat box, no problem. So here it is still running. So it takes a little time to simulate all the data here. Okay, it is still executing. While it is executing, we'll discuss our power system as well. Let me show you. Let me switch to PPT. Okay, it is executed. So this is the input and output plot which you are getting. That is the error plot. This is the input which you are getting. Okay. Once we are happy with that, actually I had to do modification here in step size here. When I will click on this setting, here I have to provide the amplitude 0.4 because the amplitude which we are taking here, you see that is the 0.4 here, right, as a reference. So leave it. Just I am showing the process how you can do it. Once you will get this plot, just apply on this. Apply and close this. Now identify the system. What kind of system it is? Means we got the output and input. Now we have to convert as a transfer function. This is the step response which you see. So we have to convert this whole system as a transfer function or as a state space model, the next step which we are going to do. So you see that what kind of system you want, as a one pole, two real pole, underdamped or undamped pair. So if you know that if you want an underdamped pair, what kind of system you have, according that you can select. Let's say I am going to select the underdamped pair. So what it will do, when I click here auto estimate, it will estimate the system here. So estimation started here and new plant will be identified. So see how many iterations it is taking to identify that system. So it is still doing. Here estimation is done, and estimation data is 89.54%, perfect, near to 100, and this is the estimated one. Okay, next thing and second thing, just apply this. When you are happy with that it is fine, then click on apply. So once you apply, we will get this plant here. See, new plant, this one. So you see that this is a transfer function, that is identified. This is a transfer function of this complete electrical system from here. Okay, now see that it appeared. We can tune it right now. So let's me tune it. What I am going to do here, up that electrical system, if I click on show parameter, you see that right now proportional value is this, integral value is this, rise time, settling time, overshoot, peak, gain margin, phase margin also it is given. And you see that system is stable as well, right? The electrical system which we designed, that is a stable system. It shows that it is stable right now. Okay, now what I am going to do here, this is the parameters which I have right now. I am going to decrease the response time from here, somewhere very less I am going to do. And you see that this is the response, this is optimizing. This is a tuned response and one is the block response. Tuned response means with the controller compensator which we added there. Aggressiveness, transient behavior also you can increase and decrease. And once you decrease, you see that kp and ki value is changed here. When I click here in update that block, so what will happen, here the block which we had here also kp and ki value will be updated. See here, kp and ki value is updated, perfect. Now I am going to run and I am going to check the output. For 2 seconds I am going to run. Okay, let me provide value 2 here and open this, and I'm going to run. Okay, right now it is 0, it is going to 0. And now see what will be in the future. So now you see it is here. So actually we forgot to modify that, but after some time it will try to achieve that 0.4 value. Not now, but it will try to achieve that 0.4 value. So actually the amplitude step response which we gave, we had to provide the value 0.4, but no problem. And you see that now it is going up, it is going to follow. You can see the difference. Now it will achieve that 0.4, means the desired output which I wanted, I am getting at the receiver end or not. So that is the benefit of using the closed loop. Your washing machine is the open loop system, your AC is the closed loop system. So what is the desired output? We give the voltage at 18 degree, 20 degree, 25 degree, right? Based on that simulated output also try to have that output, that desired output, and there is the controller which control it. Now you see that it is trying to achieve this, right? Perfect. So like this you can design an electrical system, power electrical system, and you can design the controller as well for that. Okay, so this is the output which you see. So after some time it will be achieved. And more you can modify the controller. Instead of PI you can use PID controllers also. So very in a short duration it will try. So right now the time is, it shows that somewhere 1.2 or 1.4 seconds. So within 2 seconds it will be achieve this output which we are getting here. Right, so I'm going to close this. So you got the idea and you got the flavor of that how you can design a complete electrical system with the controller, right? So let me close this. Let's switch for the another one. So this is the summary what we have done here. We have tuned this. After tuning we saw the parameters, and we tune manually from here as well, response time and the transient behavior. And once we are happy with that, we clicked here to update the block, and once it is updated here, you can simulate it again and you can check that what output you are getting from here. Fine. So what we did till now, we identify the plant model from input and output simulation data. So if you have any electrical system, you have to identify the transfer function from there. You can use that PID tuner to get the transfer function for that. Then further we use the auto tuning algorithms to tune the control gains, right? And once we tuned, we simulated and reference output which we have given, and we are getting the same after around 2 seconds, right? So perfect. This way you can design the open loop. For the open loop, what we did, we were sizing the capacitor to get the desired output. In the control system, in the open loop, sorry, in the closed loop electrical system, we were controlling the through controller. Now control algorithm deployment to TI controller, how you can do these things. Let me show you how you can deploy that controller in a embedded hardware. So first thing, you require to install the support packages. So how to install the support packages, we are going to discuss in the next session. Okay, so you once you install the support packages for the specific hardware, you will get the blocks like that. Okay, just once you get that blocks like this, we will have a blocks, and there is like analog input output, digital input, digital output blocks will be available here. So here if I switch here in MATLAB again, in this one, let me show you first of all that how to deploy it in a hardware. So this is a TI C2000 hardware. Because the model which you design, you are an engineer, you have to implement in the real world also. That's why the complete solution you have to design. Testing and deploying in the hardware, also test in the hardware that it is working proper in that hardware or not, right? So once you this is the model, and what I have to deploy this controller. Okay, and from where we will get this block, once you install the support packages. Let me move in the library and show you. Once you install the support packages for that hardware, you will get the blocks for that. Somewhere it will be here, embedded support package for C2000. So you see that when I click, we use these blocks, that from where we are giving the input pin and what is the output pin for that. Next step will be what? You will go in hardware, you will go in the here in setting, and you will choose the hardware. In which hardware are you going to deploy that model? So I am going to choose it from here. So you see that when you install the support packages, you will get the hardware options from here. Different hardwares are there. Whatever models you have, just select that model, that's all. Apply this. Once you apply that, go in the hardware tab, just click here, build, deploy and start. So this controller will be deployed in a hardware, and from this you can control that SEPIC converter for lighting. Okay, I am switching here in PPT again. So later hardware interfacing we will see in the next session. So how we address the challenges? We understand the impact of the power source and load, testing for a complete range of operating and fault conditions. We saw in this case sizing the inductor, capacitor, and understand the behavior in continuous and discontinuous mode. We check that things. Further, we designing and implementing the digital controls using only SPICE simulator tools. We use already that basic physical components to design that model, right? And we design the control algorithms also for there. Okay. More application let's say that I have to design a home energy management system. So what is happening in this model? We have a solar panel. Here we have a power grid. From this power grid, the power is going to this transformer, and from this transformer we have a home. Some loads we will have, some sources we will have which we are using there, some like refrigerators, washing machines, electricity, fans, all these things. Okay, what we are doing here, this is the complete model here. There is a solar panel, there is a DC converter, it will give the constant DC converter. This is the heavy voltage DC control, DC current, and this battery will be charging here. So once this electricity will be gone, this battery will start working. So you see that DC to DC converter is there, it will switch and it will be on, and from DC to DC, from DC to AC, it will be converted through inverter. So this is the inverter here, and this is the converter here. Once AC, you can this will be started on, right? So we have a solar panel. Through solar panel, this battery is charging, and here we have a power grid systems as well in this case, right? After that, we will end this session. Okay, one thing more I will like to show you. Let me close this first of all. Like you see that here in this subsystems, figures are added here, like there is a panel is added here, home is added. How to do these things? If you have to visualize in a proper way of your system, then how you can do that things? Okay, let me open one model from here, then I will show you. Let's say that I am going to open the full wave rectifier. What I do, this complete is a full wave rectifier. Just select this, go here, there is an option to create a subsystem. So once this is a subsystem is converted as a subsystem, I can write here full wave rectifier. This is a full wave rectifier right now. So if you have many subsystems, you can't design a complex system in a single window, right? So you can create it as a subsystem. Further, if you use the controller, you can create a controller subsystem as well. Right click on this, go in the mask, add icon images. So browse this image, wherever you have that image. Let's say that I have this image, and apply this, and image will be appeared here like this, you see. So this is the way how you can add the image also there, fine. So first of all, let me switch here in PPT again. So first of all, let's see how to do analysis of PV array. This is the PV array which you see right now here. So we'll start from the PV array, then we'll see, we'll discuss about this complete home energy management system. Okay. So it is still opening, and you know how to design this, right? If I go in the library, and if I go in the Simulink part, and Simulink part, this is the Simulink. And in the Simulink, if I scroll below, there is a wind generation. Here we have all this wind turbine array. This is a wind turbine, right? So this array I am using this. Sorry, not this one. Sorry, this is a turbine. I was talking about a PV array, right? Photovoltaic. So this is the PV array which we have here, right? Just you have to add it, and further once you add it, from here what we are giving here. Let me open this also. Irradiance and temperature we are giving it. This is a signal builder app, so you can build that signal on your own. So you see that irradiance we are giving around 1000. For the some specific time we are not giving it, and the temperature is high in this here. Temperature is somewhere 30, then here temperature is high. So from here there is an option you can add multiple signals like this in this signal builder app, sorry, block. So from where you will get this signal builder block. Sorry, it is closed. Just let me open this again. From where you will get, you can design your custom signals. Just you have to go in the library. This is part of Simulink. So if you go in the sources, so here is the signal editor, right? You can use that signal editor, or you can use this signal builder. So this block we are using. So the temperature, that is the sun heat which we are giving, and the irradiance which we are giving. When I click on this PV array, and here you see that parameters, what parameters are available for this PV array, maximum power, right? And what kind of module are you going to use. So different modules are available there. Whatever standards are available in the industry right now, all these technologies are already here inbuilt. Cells per modules, how many per module cells are there? 60 cells, or if you are working only one cell only. Open circuit voltage, short circuit current, all parameters you can provide it here. So in this case, you have to know what parameters are there. So once you get everything, you can measure the voltage on the load and all the output from here. Let me run one time and show you that what kind of output you can get from there. So this is a demux from AM. From this PB array, AM is the output. It is connected to output, and we are getting the 5 output here. So for 6 seconds I am running here. So when I open this block scope, and you know from where to get the scope. This is the PV array voltage. When irradiance was low, the voltage is also low. You can see here, right? This is the PV array current. This is the diode current. This is the irradiance which we are giving it, right? This is the temperature. So all output you can measure it directly from here. And at the load end, what is the power which we are getting? This is the power which we are getting. So if you zoom it, you can check that power. That's the power which we are getting. This is the raw power. So if you are, we have to design the converter to get the constant voltage. Already we saw how to design the converter, right? Perfect. Now about this system, HEM. This is the last one demo which I am showing you. Then we will end session. Then we will meet at 12:15. Okay. So while it is opening, if you have any questions, you can write me. Okay. This is the model. So here is the solar panel designed. Already inbuilt solar panel is already given. You can use that. This is a DC to DC converter. We saw already how to design the converter, right? And this is the heavy voltage DC current model, and this is the inverter. So we have all these blocks available. We saw already. You can use these blocks to design. This is a home energy model. So you can have any kind of here two sources, two load we are using here. Okay, this is the power grid, complete power grid model. So this kind of blocks, this is a pi one, right? So pi distributions, we have these blocks available there. So this is a 66 kilovolt load, and this is a transformer load which you are getting here, and this is a transformer which is installed here. So this is the transformer here, multi-winding transformer, number of winding on left side and number of winding on the right side. So you can provide this value like this. Okay, so let me run this first and check the output, what output we are getting. So we have to only check that when this power is off, this battery is on or not automatically. Complete model we have to check. So it is running. So for 6 seconds we are running this model. So if I go, it is still running. Let it run, then we will check that what output is coming. So different scopes are added here to check the output. So if I click here, so it is running here. You can see load on the first one, load on the second one, battery on, when battery will be on, when grid is on. So right now you see that grid value is 1, right? So grid is on. It's showing that grid is on. but we created our signal in such a way that this model that sometimes there will be no electricity, so battery will be on in that case. And this is the load which is showing you here, that which load is on and which load is off. So right now in this case two loads were on, and this both are off right now. So this is the first load, this is the second load. Right now you see that value is coming 0, so both are off. So now you see in this case when this grid is off, the value is 0, right? So you see that battery is on here. Perfect. So it will take a long time to run, so I'm not going to execute. Now you see that first load is on here. Okay, more output if you want to check, like about PB array. So here you can check that what is the voltage we are getting from that PV, what is the current we are getting from that PV, right? So like this we can design a complete power system in MATLAB using Simulink. So lots of libraries are available for that, so I'm not going to run. Actually it will take a long time to execute the full model. And here it is a battery power, solar power and load, everything you can visualize the single graph. That is the grid power, that is the battery power when it is charging and discharging, right? Grid power when it is on and when it is off. This is the solar power which you see, right? This is the load 1 when it was on, off. So this is the load 1 when it was on, how much load it is taking. When second one was on, how much load it was taking, right? Perfect. So this was the complete model here. If you have any questions, you can write in a chat box and I will reply you. Okay, just write questions here in a chat box. हेलो सर, मैं मीटिंग वेबिनार दे रहा हूँ एक्चुअली. हाँ हेलो. नहीं नहीं